Okay, for example 3, they are giving us a situation. We have an object, we have a spring, and then it's at rest at time equals 0. So at rest meaning let me determine this position to be 0. And then I'm going to pull this object down. I think it's 4 centimeters. And then I'm going to let it go. So naturally, this is going to bounce. And then it's going to go up here. And then it's going to go down. And then up and down and up and down. Because that's what the springs do. This is the position for any time t. The position meaning is going to be at 4, and sometimes it's going to be at 3, 2, 1, or 0, -1, -2, okay, continuously. So the position of this is going to be given by a trig function, and it makes sense to use a trig function because it's going to bounce between 4 and -4 as time goes by. This is an ideal situation because you know that this cannot be going on forever. But ideally this will go on forever. So finding the velocity and acceleration are fairly simple because I know velocity is the derivative of position respect to time. So velocity is f prime of t. Okay. So the derivative of 4 cosine of t is just simply 4 times the derivative respect to t of cosine of t. And that will be derivative of cosine is negative sine. So just write it in nice, -4 sine of t. And that's velocity respect of time. So you can leave it as f prime of t, or you can write it as v of t. Either way is fine. I like to call it v of t because I know that that's the velocity. To do acceleration, I just have to take the derivative one more time. So I can find v prime of t, and that will be -4 times the derivative respect to t of sine of t, which is, as you know, cosine of t. So I can write v prime of t, or I can write acceleration. That depends on t. Either way is fine. So this is how I find the functions. In example 4, I have to find the 27th derivative of cosine of x. So I'm thinking that because I have to find such a high derivative that there's going to be some pattern. So if y equals cosine of x, let me call it f of x so I can keep track of how many times I'm doing this. F of x equals cosine of x, f prime of x will be negative sine of x, and then f double prime of x will be negative of the derivative of sine of x, which is cosine of x. And then when I do that by a third time, or triple prime, this will be negative of the derivative of cosine of x, which is negative sine of x. So this goes back to being positive. And then if I take that fourth derivative of sine of x is cosine of x. And then the fifth derivative will be negative sine of x. So you see, as I'm moving up in the order of the derivatives, the answers are going to start repeating themselves. Like, you see how these two match. And then when I take the derivative of this, it's going to have this answer, and then this answer, and then this answer, and then again this answer, and so on. Since I want the 27th derivative, so since I want the 27th derivative, the only thing I have to do is find where the 27th fits in this pattern. So I know that the fourth derivative will be cosine of x, and it repeats every 4, so I know the fourth derivative will be the same as the 8th derivative, and it will be the same as the 12th derivative, and any multiple of 4 will be the same as cosine of x. So what is the closest multiple of 4 that is less than 27? and that would be 24. So I know the 24th derivative is cosine of x. So the 25th would be negative sine of x, the 26th would be negative cosine of x, the 27th would be sine of x. So I know the 27th derivative, sorry I forgot the x here, the 27th derivative of x will be sine of x, and that's how I find. Example 5 uses the fact, and I'm hoping that you know this by now, limit as x approaches 0 of sine of x over x is 1. So I'm going to use that fact. In here, I know that as x approaches 0, this will be 0 and this will be 0, so this is 0 over 0. And by sandwich theorem, we have proved that this is 1. But I don't have, I mean, this is a fact, and it works because I have x in the bottom and I have x inside the sign. In here, inside the sign, I have 7x, not x. So what I wish I had was a 7x underneath so that I can apply the same property, because what happens is the limit as x approaches 0 of sine of, let's say, I don't know, 10x over 10x, this will also be 1. And the reason why is if x is approaching 0, 10 times x is also approaching 0. So I could use the sandwich theorem again to show that. So as long as these two numbers match, the limit as x approaches 0 is 1. So I wish I had a 7x here, but I don't. So the idea is to try to recreate it. Okay, so since I have a quotient, I can say I want to divide by 7 and I want to multiply by 7. Now, because I'm multiplying by 7, notice that this 7 is not multiplying the inside of the sign. This is protected. This is inside the sign function. So when I rewrite that, I'm going to rewrite it this way. This is not sine of 49x. Please don't do that. This would be 7 sine of 7x divided by, and now I have 4 times 7 times x, which I know is 28x, but I don't want 28x. I want to keep the 7 because that's the one I need. So I'm going to write 7x, and I'm going to write the 4 right here. So actually what I'm doing is I'm taking out the 4 and I'm putting 7 instead, and I'm multiplying the function by 7/4. So that you notice if I were to cancel out the 7s, I know that I'm going to have the 4 back. So practically I'm not doing anything. Since this is a constant, it can come out of the limit, 7/4 limit as x approaches 0 of sine of 7x over 7x. Now at this point, I could change variables, or I could just find the limit right here. But this is the argument, and this is something that we have to get used to because it's included in future sections. So I'm just going to do it the way I expect you to do it. X approaches 0, okay, and that's okay. Let's call 7x, I don't know, you can call it anything you want. I want to call it theta because that's what the book calls it, and it's funny, it could have been the letter z. So if theta is 7x and x approaches 0, so theta naturally approaches 0 as well, because if x approaches 0, 7 times 0 is approaching 0, so theta is approaching 0 as well. So this is what we call changing variables. So the 7/4 takes a 7/4. Then I have the limit as theta approaches 0 of sine of theta over theta. Okay, I replace the 7x for theta, and now I know by a fact, for a fact, that this is 1. So the limit is just simply 7/4. In the last example, we have to remember that cotangent is cosine over sine, so I'm just gonna change that because I really don't know a fact about cotangent. So I'm trying to look for something that says sine of x over x, or the other one that I know, cosine of x minus 1 over x. So let's see what we have after this. Cosine of x over sine of x. Now it is very useful the fact that I have an x and I have sine of x. So I'm just going to give it the shape that it needs. So I'm going to divide numerator and denominator by x. And this is something that we have done before when we were doing horizontal asymptotes. So in here I do have what I need because this is one of the facts that I know. And then in here these two will cancel out. Now in here I have the limit of a quotient, and as you know, for properties of limits I just have the quotient of the limits. So I can take the limit of the numerator and divide it by the limit of the denominator. And that is true as long as the limit on the numerator and denominator exist. So I have the limit of cosine of x as x approaches 0. I just can evaluate it. That's not a problem. Cosine of 0 is 1. And then I know for a fact that this is 1. So 1 divided by 1 is 1.